So, hello, can you hear me? If you can hear me, unmute your mic and confirm. So, in the meantime, as we wait for others to join, I'll, uh, I'll answer the question that I have seen has been asked by Omondi. So, Omondi, did you attend the last session for kariRS? Omondi, are you there? Uh, so, did you finish the installation? Okay, so you are the guy who was on Linux, or it wasn't you? Okay, okay, okay. And okay, one more question. Do you are you familiar with Docker? Do you know how to use Docker technologies? You're familiar with Docker? Okay, okay, okay. But we'll be having a Docker session very soon for kariRS, and I think it will help you. But again, to answer your question, let me now let me first go to the terminal to answer your question before we start. Let me share the screen. And so here I'm on the terminal. Can you see my screen clearly? Is it clear? Is my screen visible to all of you clear? Okay, so now I'm assuming that you have installed kariRS, and following the steps that we did last time. So can you confirm that when you write kari hyphen hyphen version, I mean, sorry for version, do you get to see what I have on the screen? Let me repeat. Does it display this? Pardon? Right now, can you see it? Can you see the command? Okay. When you run that command in your machine, what do you get? Yeah. So that means already kari is installed in your system. So the next thing is I want you to type the following command: kari doctor. Kari doctor. That's the command that you are supposed to have uh, run before doing any other thing in kariRS. Do you get to see whatever is written on my screen? Yes, all dependencies are installed. So yeah, so you are ready to you are ready to use kariRS. So now from there, eh, so your question was, what is your question specifically, or how to start a project? Okay, so just a minute, I check whether there are other two so that I can. Just a minute so that I can allow other people to join the meeting. Yeah, so uh, let me take you through how to get started on the project. So, okay, now right now I'm in a folder known as Rust. Now let me, when we want to build a new project, you use the command kari, then you use kari new, then you specify the board that you want to use. So for right now, I can, if I'm on a mega, I can use mega. If it's uno, let me use for example, for mega, pardon. Eh, I'm typing the commands the PowerShell. Anyone else not seen my screen? Okay. Um, let me carry new. You can see what I am typing in my command in the terminal. So yeah, then you give it the name of the project your project. For example, I could decide to call it timing. Like today we are going to deal with timing, so I can decide to call it timing, and then I click enter, and you can see what it tells me. It has created a project for the mega board. The project name is timing, the board is mega, the board rate, and all those things have been set. Now from there I just have to enter into that project. So I cd into timing, and inside and inside I can see the project structure. Everything about the project structure was well discussed in our last session. So have I answered your question, or do you still have any other question? Okay, so for that session of how to get started, it is well it is well documented here in the documentation. Let me If you visit the documentation page, we have this session for the kariCRI. So it is the first command here, karinew. So this is the command we were using, karinew. So it is the one that creates for you the kariRS project. So you give it the name of your project and the board that you want. You can either use hyphen board or the short form of -b to tell it the board you want. Now, if you want to know the types of board supported currently for this, for the current version of kariRS, it supports the following board names. You can use Uno, you can use Mega, you can use Nano, or you can use Leonardo. So it currently supports the most used boards. With a number of boards will coverage will greatly extend as kariRS evolves. So that's how you build your new project. So then from there, you just cd into the directory as I showed you, and then the next step is to cd then into the source, as I will be showing you how to go through. Now, for example, we have already created that project for timing. So let me share the screen again, for the entire screen, so that we can move ahead together. So this is the current. If I ls, you can see this one is a project known as intro to session, the one that we had last time. So you can see inside this is how the project looks like. This is how the kariRS project looks like. So it has this folder known as .build. This one is automatically generated when you compile or you build your project. So it is initially not there. So it is here because we had compiled this project in our last session. Then the next one is .cargo. This one is part of the configuration of your project, so you do not deal with that one. And then we have these other files. These are just configuration files for kariRS. So once you are in a project like this one, you have to enter into this source folder. This is where you will do your work. So you enter into source, cd, you enter into source. So this is where you'll always do your work. And here you'll find two files. We have this file known as karientry.rs, and we have this file known as main.rs. Now, karientry.rs is what provides the abstraction layer for kariRS and everything. So you by all means, you do not modify this file. Your business is in this file known as main.rs. So that's what we'll be doing today. So I have opened this folder using VS Code. Now, for those ones who have VS Code in your system, you wanted to open a project into VS Code without first going to open VS Code directly. You use the command code and then a full stop. That's how you open VS Code. You tell VS Code to open your particular project. But you can use any code editor to write your code. Although VS Code is the recommended uh, is a recommended IDE to use with kariRS, as it is helps you a lot in auto completion and all that and all those things when writing kariRS code. So now this is what we had last time. This is where we stopped last time in our last session. So before I continue, anyone who has a question, if maybe whatever is showing on the screen is alien thing to you, if it's completely new or you need a clarification on anything, maybe you've forgotten something or you did not get something right last time or you are completely new, is there anyone with a question? If you have a question, just unmute your mic and go ahead and ask the question that you have. Yes. uh, yes. uh, Let me go back and let me cd to what we have created as you have been looking, and let me cd into source and ILS. So you are saying that your source folder doesn't have these files. Yes. Are you there, Omondi? Omondi, are you there? So it sounds like we have lost Omondi. All the other people's present. Anyone to unmute the mic and confirm whether you can hear me and see my screen? Olivia, can you hear me? Okay. So with that, we will just go straight to beginning today's session. And so I'll share my entire screen. Now, when sharing my entire screen, I can't see your reaction. So if you have any questions, you will just have to unmute your mic and ask. So let me share the entire screen so that we can uh, continue with the session. So last time in the intro section, we did look on how to on what kariRS is and how to maneuver into kariRS, and we also wrote a program to blink an LED, and we stopped at the point we were to do it asynchronously, and so that's what I will be answering today. Now, to follow around, I've sent you in the comment section. I've sent you the link to the actual section of the kariRS documentation in which we shall be looking into today. So that section is this section known as advanced macros. So that's where we shall be heading to. And this is where we shall now be really moving from the traditional way of writing microcontroller code into the modern way of writing, or the philosophy of kariRS and how kariRS recommends that the code in it be written in order to ensure we have high efficiency and we are able to do a lot with our microcontrollers. So last time we had this program. So for the sake of those who could be new, I'll move fast about this program. So this program was meant to blink an LED, and we were using a Mega board. This project was configured for the Mega 2560, and this line of code here, pin mode, is the code that initializes the pin we want to use. We are telling kariRS what pin we want to use in which pin of our board we want to use. So that's what pin mode actually does. And the structure of kariRS is that we have the init structure. This is where you write your initialization code, and we have the run function where you write the code that will be run continuously. So that's the structure of kariRS, and you can see that the logic that is run continuously is confined or is restricted inside the logic that runs once. But again, you cannot come and write code below it. You cannot come and write code here where I'm typing you cannot come and type code there. All code that is to be run once needs to be written before this section. Again, we said in kariRS, you can name this function whatever you want. For example, this function is named setup. I can name it whatever I want. For example, I can call it Vincent. I can call it start. I can call it whatever I want. By default, kariRS generates it and gives it the name setup to help you understand what the function does. Also, this function here, I can name it whatever I want. I could call it even Hulk. I could call it whatever I want. Provided I just give it, I can even just call it R, and kariRS has no problem with me, provided I give it a name of the function. So the thing that matters most is this annotation. These annotation are the most they are the powerful things in kariRS. They are known as macros, and they are the ones that make all this possible. They enable kariRS to do all that you see it doing. You can name your function whatever you want, and kariRS will go ahead and organize your code during compilation and do the right thing, and you will have your program working. So I'll go ahead and clear this, that we can understand what's actually happening. So let's visit the documentation so that we can see what we'll be dealing with. So kariRS provides a set of advanced macros for scheduling, sequencing, and hardware convenience. So it is noted in the documentation that these are optional but powerful tools for more complex applications. These are optional but more powerful tools for complex applications. And so we will first see why they are optional, but they are the recommended way to do things. I recommend you, once you understand this, forget the other traditional way of writing code. Forget the blocking way of writing code. So kariRS has the scheduler known as kariasync. And the kariasync, how it works is that it takes in a function, a closure. This function is known as a closure. This is how it is written. And then you tell it the interval. You tell it the interval in milliseconds. What the interval here means, you are telling kariRS, I want you to run this block of code after this amount of time. For example, if I could use the example of a blinking LED, we always see the blinking LED blink. Maybe if you wanted it to blink after every 500 milliseconds, you want it to turn on, then off, then on, then off. When you write your code in the manner that we saw last time, I would like to show it. Let me type this quickly so that I can explain using what we have seen with the blocking manner. So when writing the code in a blocking way, this is how you write it. I'll use this example for blinking LED so that you can understand this concept of what we are actually meaning when we talk of asynchronous task. So I write there 500, and I can write here delay maybe for 500. I want them to be, so this If you wanted to blink an LED, literally this is what you'll do. This is how you light. If you compile this code and upload it to the microcontroller, it will blink the LED that is on pin 24. Now let's understand what this code first does. Now this digital light, it turns the pin 24, it turns it high. That is, it turns whatever is connected to that pin. Now in our case, we are assuming that we have connected an LED. So LED here turns on, and here we say LED turns off. So we are assuming our load is an LED. It could be any other thing. It could be any other thing. So assuming our load is an LED and it's connected to pin 24, the moment the program encounters digital lights, high means turn it on. You give a voltage to that pin. So our LED will be on. Then you tell the microcontroller to delay for 500 milliseconds. Now, and after delaying for 500 milliseconds, you tell it to turn it off. Sorry, this one should be low, like that. You tell it to turn it low. So you tell it to turn it low, and then you tell it to delay for another 500 milliseconds. That is half a second. So let's understand, what does this code really mean? Turn the LED on, then delay, and then turn it off, delay, and then repeat, because the run function keeps repeating. After it has finished executing whatever is written here, it repeats that sequence again. That's why we call it, that's why it is the loop section of kariRS model, architecture model. So we want to understand what is actually happening when we light delay. What actually happens is you are telling the microcontroller, I want you to stop, to just be idle. I want you to be idle for 500 milliseconds. So during these 500 milliseconds, your microcontroller is literally doing nothing. It is just sitting there waiting for 500 milliseconds to end. It is just sitting there. It's waiting for 500 milliseconds to end. Once they are done, it then comes here. It turns the LED off. Then it sits idle again for 500 milliseconds. So it's there waiting. It's doing nothing. Now, if all you want to do in your project is to just blink an LED, then you can see that this code is correct. But now, that's not the case. You are learning these skills to build or to use this code to solve real world problems. Now, let's assume you are collecting data or you are measuring data using sensors. So let's say below here you have logic for let's say maybe you are your logic for a temperature sensor. Maybe you are measuring temperature, and maybe also you are also using an ultrasonic sensor. You are measuring distances, and then you have a logic for actuators. Actuators here could be motors, or even sending data to the web and all that. So now let's see where disaster comes in. Now, if in your project you had some LEDs, you want to do something to do with LEDs, maybe you have them as indicators or something in your project that they show that something is going on in your, they are showing that something is going on in your code, or they show that your system is running or whatever you've programmed them to do, but they are having these delay functions. Then you'll have a disaster, because if this LED has to be blinking when your project is running, and when it is at this period, when you light delay, the microcontroller is idle. Then at this idle state, remember the temperature sensor is still measuring temperature and it is sending that data to the microcontroller, and the microcontroller needs to act. It needs to act and respond to that data from the temperature to do whatever you've programmed it to do. The ultrasonic sensor connected to another pin is also taking on data. It is measuring distances. It is telling you, oh, these distances, everything is still continuing, but the microcontroller, the brain of your project, is asleep. It is not responding. So if it's supposed, if it is something like, for example, an RC car, you're designed an RC car, and it is supposed to detect distances to prevent collisions and all that, it will not be able to do that. It will just collide because the brain is asleep. The microcontroller is asleep. It is waiting for these delays, and after these delays, it is when it will come and respond here. So this program here will delay the execution of this because you are telling the microcontroller to be off, to be sleeping. So this is very bad, and it is a bad coding way of doing things. You cannot, if you want to build a project that's solving real world problems, you cannot be using delays, or you cannot be doing things like this. So this is where we now want to see how can we let go of this, how can we take away all this, and maybe if make sure that this code which I've given as an example, any code that has a delay is a blocking code. I've just given an example with an with turning on and off an LED as an example. But if any other code that we will be writing other codes, I'll be showing you the blocking and unblocking code, you will realize that any code which has a delay, if you are doing more than one task, it will block the other task. So that is what we are talking about. If all your program is doing is one specific task, for example, just blinking an LED, if it was doing just this one task, then you don't need, you can just stick around with the blocking code nature. But if your project is doing a multiple task, it is measuring temperature, it is measuring distances, it is controlling motors, it is doing this, it is doing a lot of stuff and you want them to be done at the same time. You want the microcontroller to be ever active, ensuring that everything in your project is doing well. For example, maybe you are designing a smart agriculture system, and you want every time that you want that each time that the pH is measured, maybe you have an indicator that shows. You cannot be using delays in your system at any point. You do not want to use delay. So that is what we want to see. How can we basically get away with this blocking code nature? So this code here, I will comment it out like that so that we can see its equivalent. I won't first delete it, I will comment it out. So now let's see its equivalent. Now back to the, let's go back to the documentation, and this is where I was explaining about kariRS. Now we use what we call a scheduler. So a scheduler basically takes the task you want it to do, it takes the interval, and it takes the name of the task. You have to give kariRS the task name. So the task is known as a closure. This syntax is known as a closure. And basically this is how you can see an example given in the documentation. And yeah, that's how kariRS does. But let's do it ourselves now. So are we together up to that point? Anyone who has a question up to that point? Anyone who is confused, who is lost or wondering what is even going on? Yes, Wesley, can just unmute your mic. Yes. Yes. Okay. Yes, and actually, for those who missed last time session, we have we also have a recording for that session. Let me share it very fast. Although we also we be as we continue with kariRS, we'll also be having various occasions where we'll be doing things, and you as we recreate and create projects, you will see where all this code came from. For example, what did I share to you? I'm sharing you the documentation. Let me share with you the just to answer you. Yes, let me share the link to the recording for the last session, so you can watch it later and you'll understand where this code came from. But just to answer you, this code you see here, this whole code, you that should not worry you at all. All these syntax, all these things I'm highlighting, they are automatically generated for you by kariRS. When you create a new project, all these file structures, everything, they are automatically generated for you. Your only business is to just come and write the code inside these functions. But again, once you go through the recording for last session, you will get to understand everything. Let me share it right away in the comments. Let me share it right now. So I've shared it. I've shared it in the comment section. You can click on that link to access the link for the session for last time. So have I answered your question, or do you have another question? Okay, thank you. Anyone else with a question? Okay. So someone is asking about let me just check it out. Really. That's asking about exemplar. Okay. So why should you use what's the difference or advantage of using kariRS instead of other schedulers like Zemfil and all that? So that boils down to why we are even using kariRS. So kariRS is not is not uh, is not something that has come to to swap or to replace other schedulers. We have other very amazing schedulers and other very great frameworks, but kariRS has not come to replace any of that or to come and like fight with them. It is providing with you with an alternative. And the thing about kariRS, is that this framework is based on the Rust programming language. Now, for Zenfil, I don't think it's based on Rust. The one who was asked that question, Francis. Francis, can you unmute your mic? Francis, are you with us? Okay. So, okay, thank you for answering. So that's actually what we are trying to answer uh, with kariRS, and I knew this is something that is raising questions as to why should we even use kariRS. So basically, the reason it's not that there's much more of a greater advantage when it comes to how the scheduling works, but what kariRS gives us as an advantage is that it is based on Rust. Now, the fact when you look at most of the frameworks that we use for embedded, they are based on C and C++. And the weakness with C and C++ is when it comes to learning robust projects, memory safety becomes an issue. You run into memory leaks and all those issues. But in Rust, memory leaks are something like over history because of the Bola checker and all that. And previously, if you wanted to write code in Rust and do the things that we are about to do right now, it would you could sweat. Like it was literally tough and hard, and that is what kariRS is trying to bridge. It's trying to bring about Rust in a way that is friendly to everyone, because it is you find that most of the programs that have been written in Rust, actually even after this you can check out, you realize that apart from kariRS, being able to write code in such a simple manner that like we are writing right now with kariRS is practically tough if you have no deeper knowledge with Rust. Like most of the projects that have been done with Rust previously need a person who is very expert in Rust. But we want to bridge that gap. For example, when you look something like Arduino, someone who has no programming knowledge can learn it very fast. He can adapt fast. That is what we are doing with kariRS. But kariRS is bringing even those advanced scheduling concepts and making them easier. So I hope I have answered your question, Francis. I cannot, I'm sharing the entire screen. So if you have any question, just unmute and ask the question or reply to me. So anyone else who feels they have a question? So let me, who is asking that question? Omondi, I tried to reply to you. You were not responding. I was answering your question. So, for example, you can see my screen. Let me go through that first. So you can see my screen. We are in the intro session. This is the project that we are in right now. If I ls, now for those ones who are ultimately new to the terminal, ls means list. So we are just telling the computer we want to see what we want to see the list of files and folders in which we are it. Again, all this has been discussed in the previous session. which have provided the link. But I would urge you so much to focus on this session. This one we are doing right now is more of a core. If you are looking forward to being very good in kariRS, focus much more on this session. Then you will look into the previous session and see the introduction part of kariRS. So right now, when you have started a project, you should be having these things. Now for you, because you have not done any building on Monday, and I want you to confirm, you should be only be having this, what I have highlighted. Is that what you have inside your project? Um, can you try build? Can you try creating a new folder again? And if you still encounter that, you let me know. Yeah, do that. As I continue explaining, do that, and once you see it's not giving you the correct output, you let me know, so that I can then answer to you, so that we can continue with the timing, and then I can answer to you. So this is the, I hope this is what you're, this is the command you write. I've highlighted it, carry new uh, -b for board. You tell it the board you want. I have shown you the number of boards we have: mega, uno. For us here we have used mega, and then you give it the name. Try learning that command, and let me know what you have. Okay, try again, and then let me know. Now, to continue with what I was actually explaining here, is that now we want to execute asynchronous code, and I need to make this concept quite clear of what we call asynchronicity in. There's someone whose mic is on. Kindly, you could turn it off. So now let me show you why. Before I even continue, let me show you why it is very important to even use VS Code with kariRS. Now, the moment I start typing, you can see it gives me options to choose from. So I know I want this scheduler carry async, so I just click enter, and it does the auto completion. That's the beauty of using VS Code with kariRS. So now we have this scheduler known as carry async. But here I want to make one point clear, which could be confusing. If, for example, you have done scheduling, or you have done things to do with RSOs and all those things, and a scheduler that like the one was being asked about here, I need to make the concept of what the concept of asynchronicity in kariRS, what it actually means. So carry async here, remember this code we are writing here will run on a microcontroller which has only one core. So it processes everything in one core. So we are not dealing with a multi-core processor like the one in your PC, which has like 2 cores, 4, other 6, and whatever. We are having one core. So the microprocessor cannot be doing many things at the same time. It has to do everything at a time, everything at a time, everything at a time. So what do we mean when you say that this microcontroller can do tasks at the same time? What do we actually mean? So kariRS leverages on the concept known as interleaving. The concept is known as interleaving. So what we are doing is we are taking the microcontroller and we are telling it this way. When, for example, if we had this, let me give an example with this code we have here. When the microcontroller turns this LED on here, instead of being idle, we tell it, you turn this on, then maybe jump and come to this task and be attending to these ones. After these 500 microseconds are done, then come and execute this. So instead of being idle at this point, be doing something. We don't want you to be idle at any time. That's what we are doing. And because of that, that time slicing, that multitasking, then the microcontroller, because it is doing it at very great speeds, so it happens like the microcontroller is doing things at the same time. So that is something I wanted to make it clear, because when we talk of the concept of asynchronicity, that is asynchronicity, we can asynchronicity can be achieved in that method, or it can be achieved in another method known as uh, parallelism. So here I'm taking you into deeper concept because I want you guys to be good in these things. So parallelism is whereby the processor you are using has many cores. For example, your computer or laptop can have 2 cores, 4 cores. That's why you see if your friend could be having the same laptop, but their processor has many cores, they can be able to do multiple tasks. Their processors appear, or their laptops appears to be faster because the processor can be able to assign the various cores task. But here, because we have only one core, we will be dealing with microcontrollers which only have one core. A core is a unit of processing. We are only having this one unit. These hours, we only have one unit to process the data. So we cannot use parallelism. We use interleaving. So interleaving is also another way of achieving asynchronicity. So if someone ever asks you, how does kariRS be able to achieve asynchronicity, just tell them it uses interleaving concept. It just does interleaving. It schedules the task very fast. So it just avoids being idle. That's basically what we are telling the microcontroller to do. And that is what kariRS does. Behind this one line of code I've written is a smart algorithm that does all that for you without you having to think much more about it. So we will assign it a task. So this one here is a closure, and it is what we call a task. In kariRS, we call it a task. So this is a task. This is where all your code will go in. Now, when you assign a task, you need to give it a time. You need to tell the microprocessor, uh, this task that I want to be done, I want it to be done at which time intervals. If, for example, I wrote 1, it would mean I want you to execute this one after every 1 millisecond. That is like executing it continuously, because 1 millisecond is a very small amount of time. So for us, we could decide to go with 500 milliseconds so that we can see what is actually happening, and then you can give it the name. I can call it task 1 because we'll be creating a couple of tasks. So this, whatever code I shall write inside here, inside of this closure, will be executed after every 500 milliseconds. So this is what will happen. When you power your microcontroller, it will come here, it will see this function, it will execute the initialization code, and then it will enter into the loop code, which is the run function. Once it enters inside here, it will then meet curly async. And once it meets curly async, the discussion here is what do you want me to do? So it finds that you have told it, I want you to execute this task after every 500 millisecond. So it will know this task, if I execute it right now, I cannot execute it again until 500 milliseconds are done. Now, during that time interval, before 500 milliseconds are over, what else can I be doing? So that's what we are addressing. So the microcontroller can be doing something else down here. Maybe if you have written other codes here, it can be executing those codes as it waits for the time for executing this task to arrive. So now let's see how we can blink an LED using this kind of structure, because again you realize that we cannot use digital lights here. We cannot use it, that's kind of logic inside here. If I was to take this code, for example, if I was to take this one here, now you see the disaster that comes in. This code is only executed after each and every 500 milliseconds. So if you're telling it inside here, I want you to turn this high, it means it will always remain high. So when will it be turned low? And even if you try to think, oh, maybe I could take this one and maybe bring it here, it means the LED will be turned high and low in one execution time. So you'll be doing something that is not sensible. So you realize that you cannot now turn on the LEDs in this manner. Up to there, are we together? I'm just giving an example with turning on and off LEDs. But I want to ask, is there anyone who is lost up to that point? Okay, let me repeat. I've said this carry async here will execute this function. This let me write it here. This is what we call this here is what we call a task. So when carry async, when the microcontroller finds carry async, it comes and checks this time here, and it says, oh, this task, when it is registering the task, it will register it as this name and it will register it with its time. So it knows after each 500 milliseconds I have to execute this task, that this one will be executed once. So I cannot if I wrote this kind of code, I told it turn this high and turn this low, what would happen is that the LED would turn high very fast and turn low very fast. So most of the time your LED will appear to be low because it is high, low very fast. So it would never be, you never even see it high, because there is no kind of a delay between the high and the low, because this is an unblocking. You cannot come to, if you came to light delay here, you would be breaking the logic of even having an unblocking code. So you cannot use this digital light to do that, because this one would execute immediately, and immediately it has executed, this one would execute, and after this one has executed, you are done with that task. kariRS knows, oh, that task is done. Now I need to wait for another 500 milliseconds to execute this task. And if I'm going to wait for another 500 milliseconds, and I already turned off the LED, it means for those 500 milliseconds, this LED will be off, and that will be repetitive. This LED will always be off. The only moment maybe you see it on will be so fast that even your eye might seem like it has blinked. It won't give you the actual result that you want. You want it to be high for 500 milliseconds and off for 500 milliseconds. Have I answered your question? Anyone else who has not understand what we are talking about? So now, uh, I have just gone to the concept of LEDs with a reason, because I want us to learn uh, to learn some new things as we learn with this schedule. I want us to cover a lot. So uh, I will be also showing you a better visualization of what carry async does. I'll be showing you in a few, but let us start with the LED, so that when I'm showing you the visualization, you'll be trying to link it with whatever we are doing. It's like we are going from advanced to the simple. So that is, instead of the simple to advanced. So that's what I'm kind of trying to do with you here, and I believe you'll understand it well. So we cannot use digital light anymore. So we'll say bye bye to digital light. That is the analog way, is the traditional way of doing code. If you're coming from Arduino, you know that is how you turn on and off LEDs. And now we introduce another concept of state. Now we will introduce states. Now, when I talk of states, I'm trying to bring you into a picture. If we want to blink an LED inside this thing which is non-blocking, we need a way to turn off, to play with state. We want that when these things execute, it checks if that pin high, is that pin high. If it is high, turn it off. If it is off, turn it on. That is the kind of logic that can excel inside non-blocking, because non-blocking wants to, it just execute. It is no, there's no delays. So the processor wants to, the microcontroller is coming, executing, moving to the next task, executing, moving to the next task, the next task, the next task. So it doesn't, there's no delays. So how do we toggle states? Now we want that every time this thing is executed, if an LED was on, turn it off. If it was off, turn it on. That is the only way you can do that. So that's why I will introduce you to this other macro or other functionality known as kariRS. Now these APIs I'm explaining to you, they are the asynchronous APIs. The likes of Akina Digital Right and all those, they excel in the non-blocking, and you will see areas where you can use them in non-blocking, but most of the time you use them in the blocking code. But the recommended way is writing non-blocking code in order you can exploit kariRS to the very best. So we'll be looking into this API known as kariRS. So kariRS takes two parameters. It takes a pin array and it takes the pulse name. So you can see how the documentation says it toggles all the pins high or low on each invocation. So each time you call kariRS, it toggles the state. It toggles between high and low to the pins given. And you can see it is useful for flashing LEDs or toggling output. It's very useful for toggling output, as we will see. So we give it a pin array and we give it a pulse name. So let's understand what is the documentation trying to tell us when it says that way. So you've understood that, so let's clear that. So we can write here carry pulse like that. So you can see when I try to save that code, it says index out of bounds because the len is 0 but the index is. Now this kariRS, it takes in an array and it takes in a pulse name. We can call it pulse1, or you can name it whatever you want. So that is how its syntax is. Now this array here, this one is known as an array. This is how you write arrays in Rust. You use this square bracket. So inside of here is where you pass the number of pins that you want. You can give it, for example, our pin is 24. But if we had many pins, we could give it 24, 25, 1, 2, whatever number of pins you have, you'll give it. And you have to make sure that the number of pins you're giving it here have already been initialized here. So that's where we use kariPulse. So what will happen here is that each time kariAsync, this task is executed, this task 1, this whole of this is task 1. When task 1 is executed, the microprocessor will check, what should I do in task 1? I should just run kariPulse. So it will take this pin and change it. If it was high, it changes it to low. If it was low, it changes it to high. And because this task is executed after each 500 milliseconds, then what you have is what? You have your LED blinking on and off after every 500 milliseconds. We'll be uploading this code. We'll be uploading this code so you can see what you are meaning. Now let's visualize what we are actually meaning when we talk of this. So let me clear this and let's introduce another task. Let's create another task. and let's say this one runs after each 1 second, and let's call it task 2, like that. Let's create another task, and let's call it task 3, and let's say it runs after every 1500 milliseconds. Now, for simplicity, so that you can first be able to understand what we are doing, I will comment out the LED example and be left with these two tasks. And actually, I can just let me just call them 1 and 2 so that you can to first give you the visual. Although they can remain as they are, 2 and 3, whatever you want to name them. And let this one remain. Yeah, let it remain as 1000, and maybe let's make this one 1500. There is no problem with that. So I want us to understand a very important concept. So I want us to visualize what happens. So I will initialize our serial. So use 9600. So we didn't cover, I don't know whether anyone who was in the last session, we didn't cover about the serial, but this is how you initialize the serial in kariRS. So I told you in this session you learn various things, but the most dedicated thing about this session is the timing or the scheduling procedure of kariRS. So this is how you initialize serial in kariRS to start the serial monitor. So you call this macro known as serial, and you give it the boundlet. The boundlet means the rate in which your microcontroller and your PC, your computer, will communicate. So you need to give it a boundlet that is supported by your microcontroller. So 9600 is a common boundlet that is supported by AVR microcontrollers like Uno, at Mega 2560, at Mega 328p, all of them, they do support this 9600. So this is how we will initialize it. Now I want us to print in our terminal. I want us to print something. So for printing purposes, we use a function known as k println, like that. That's how we print to the terminal in kariRS. This k just means kariRS or kari, and then we have print line. As you can see, it's like that. Print line. So here I want us to say to write here, this is task 1, execute each 1 second. Okay, that is what I want us to write. Then inside of this other task, we write k println, and we say that this is task 2, execute each 1500 milliseconds. Actually, you could just take this one as milliseconds, like that. After each 1 millisecond, like that one. I mean, 1000 milliseconds. So you might be wondering, what are we even doing here? What is actually happening here? So this is our task 1, and this is our task 2. Now, if we were to compile this code, of which we will do compile, what should happen? Now, before we compile it, upload it to the microcontroller and see what happens and what the microcontroller will print to back to our computer, we need to understand and anticipate what will happen. What do we expect to happen? Now, this is what should happen. At 0 seconds, we will have nothing. We should have nothing. Nothing should be happening. Now, at 1000 milliseconds, we are talking of milliseconds. After 1 second, we should see this one being printed. This task should be executed, thus it will print this one. Now, after 1500 milliseconds, we should see this task printed. Actually, even to make it more simpler for you to visualize, I can make this one double of this one so that you can understand. So after 1000 milliseconds, this one will be printed. After 2000 milliseconds, this one will be executed. So at the 1000 milliseconds, it will means task 1 will be executed. Now, at the 2000 millisecond, after 2000 milliseconds have passed, we will have task 2 executed. But here is where something amazing comes. At the time that 2000 milliseconds are ending, this task will be at its second cycle. It should also be executed at that time. So this task will be executed, and then the MCU will run first to task 1. So they will appear that like they have been executed at the same time. So this is what will happen. This one will not block, they will not block each other. So the MCU will do that. Then we continue, and we have after 3000 milliseconds, we have task 1 executed. And then at 4000 milliseconds, we have task 2 and task 1 executed. So I've doubled this one deliberately for you to understand. So even when you are doing your timing logic and what you want to do, you realize if I do this timing, if I put it this way, will these times ever overlap? So you can see if you made this one, if you made this task to have double the time of this other one, they would overlap. Now, what if we go back to what we had? If this one was 1500, so this one would still execute well, whatever we have here. But now let's see what happens if we go with this other version. So we make this one 1000, 5000. So at 0 second, we have nothing is executed, nothing has been registered. After 1000 milliseconds, so this one should be executed, task 1. Now at this point, we will only have task 2 being executed. Then at this point here, we'll have task 1. Then at now we were at this point. So at 2000 milliseconds, just milliseconds, we'll have task 1 executed. So task 1 has been executed at this time, it has been executed at this point, but now at 3000 milliseconds, something amazing happens. At this point, 1500 milliseconds have passed, so task 2 is supposed to be executed. But again, our task 1 will be at its third cycle, so task 1 should also be executed at that particular point in time. So the MCU will cycle very fast to make sure it executes this one and executes this one, or it executes this one and executes this one. So that is left for the MCU now to, according to how you've written your code, it will take either task 1, execute it, then go to task 2, take task 2, go to task 1. That is at the point in moment when they overlap. So this is a very important thing to understand, so that when you are writing code, you know what is actually happening. So again, for simplicity, okay, let me take this one back so that we can compare it when I upload the code. for higher simplicity, let's make it this one 2000, so that you can understand very well what actually happens. So I'm going to save this, and now I'm going to go to the terminal, and I'm going to clear. So I'm going to connect a board here. I have a board with me. So just to show you the board we are going to be using. So we're going to be using this board. This is the uh, Atmega 2560. So you can see it is powered on. This is an inbuilt LED which is blinking here, but right now we are not dealing with the LED. So this is what we're going to be using. That's why I configured the project as a Mega 2560. And actually, if you want to know how your project is configured, let me again go back to sharing the entire screen. So if you tend to know how what is the board being configured for your project, you could go to here carry.html file, and here you see we have this section known as the board. So current you can be able to edit all this, but for the current version of Kari, if you are to edit this board name after generation, you would have incompatibility issue with the fight with kariRS, but that will be well much catered for in the coming version of kariRS. But this is how you get to know what kind of board you are using. So if you go to kari.html, this is a configuration file, so it gets to show you what kind of a board you are using. For the baudlet, if you change it, there's no battles. kariRS won't fight you. You can change it. You'll see even commands for changing this. Even the name, you can change it. You can either come and edit it here manually, or you can tell kariRS that you have changed the project name and it can do it for you. We'll be seeing how to do all that in the coming sessions. So now we have already seen of this. Here we needed a semicolon like that. You can see Rust is already shouting at us. We've not done that. So now this code should, so we should see this one print after 1 second, this one after 2 seconds. So let's go to the terminal, and I will do kari. Now, here is something that I want you to know. I have connected my board to the laptop, but I do not even know which port. Remember, you need to know the port that your microprocessor is connected to. Okay, so let's go to kari. If you have any question, you can just unmute your mic and ask. Remember, when I'm sharing the full screen, if I try to go back to the session, you'll see those multiple screens appearing on your side, which is not quite visual appealing. So now I have connected the board into my computer, but I do not know the port in which it is connected to, which is very important to know if I want to upload my program to the microcontroller. So kariRS caters that for you using a command known as kari-detect. Now kari-detect will basically check in your all the ports which have been provided, and it will check for the ports which have microcontrollers connected to them. Remember, your computer has various ports, so it will check the one that has a valid microcontroller. That kariRS has this logic of checking and knowing which one is a microcontroller, which port holds a microcontroller. So I'm going to run kari detect, enter, and you can see directory. It shows me that there is an Arduino Mega 2560 connected in COM9. So this board is known as Arduino Mega 2560. That's what it is named, and it is connected to COM9. Once I know that, I can go ahead and tell kari. Now I could decide to build the project, and then I can, if I run kari build, it will build the project, it will compile the code, but it won't upload it. To upload it, I would then have to go and do kari flash. I tell it hyphen port, I tell it what we have seen there, COM9. That is what I would do. But again, since I am very sure I don't want to do the two stages to build and then flash, kariRS provides another command known as kari upload, which will do those two commands at the same time. So I just need to give it the port like that, and I just enter. So it will build. So you can see here, it says finish release. So it has already finished. So it said you project build successfully, and then from here it then uploads the program. So it says your program was flashed successfully. So that this command, the kari upload command, does all of them at the same time. So if you've not gotten, this is the command kari upload -p COM9. And if you are the person who is not you do not have shortcut, you do not have abbreviation, you can just write hyphen port COM9. It's all the same. This one is the same as writing -p COM9. It's the same. It's just the same thing. So now, after we have already programmed, but we need to know to see what is being shown, what our microcontroller is sending to. We need to see what it is sending to our laptop. So to do that, we come and say kari monitor. So kari monitor tells you need to specify a port. You need to tell it what port should it monitor. So you need to tell it, I want you to monitor COM9, the port that we had. So it tells you that it has been connected to COM9 at this baudlet, using this baudlet at 115/200 baudlet. So now let me, if you wanted to leave this one, you can press Q. Now you can see there's an issue that has happened. We can see we have an issue in printing. So why is this happening? This is very important for you to understand. Why did we have an issue with that? Now let's go to what we have in our code. We are telling Serial that we want to use 9600 as the boundlet, but our kari.toml is telling kariRS we want to use the boundlet 115,200. Want to use this baud rate, but the code is telling kariRS we want to use this boundlet. Now kariRS has to decide who decides the boundlet which to use. Now by the priority that has been given, this one, the kari.toml is more superior than the code itself. That's how it operates. So here it appears like kariRS sees as if I did not give anything. It feels like I did not give anything here. So it does not even consider what is written here. So I hope you have understood that. So once we write this one here, if we write this one as 9600, we will be conflicting with the carried on tumel here, this one here. So we have to decide which one what should be taken into consideration. So we could try. I want I want to show you the kind of mistakes that you could make. You could come and say, why don't I make this one 9600 and save it, and then try to come here and compile my code, because you need to compile the code once you've changed things, and you upload it like that, and you try to open the monitor. So you can see what has happened is that now communication happens at 9600 baud rate. So that is why I was telling you the baud rate here is what is taking superiority, though this behavior will be deprecated in the coming kariRS version to bring back superiority to the code. So right now the superiority is in this file for the baudlet. Only the baudlets in here in carried on toml takes superiority over these ones in the code, which actually is not something you probably want, and so this behavior will be deprecated. Again, take note of that, it will be deprecated in the coming version of kariRS. So but for the current version, now you know, if you want to change anything with baudlet, you just come and change it in carried on toml. You come and edit here, you change the baudlet here. So if it's 9600, if you want to go with 9600, come and edit it here, and you won't be fighting with carry. So that's actually what you should be looking forward to. So let me now show you something that we need to. Now let me restart the MCU, or let me clear, and let's go start with the monitor. Now I want us to understand something very interesting. Now after 1 second, we see this one is executed. Then we see task 2 is executed, because obvious, when we come from 1000, we will go to 1500. Then from there we will go to, now this task 1 will also be executed. Now you realize now this one would be confusing to understand, so we will do something which is very important. We will come here and say, instead of having instead of using these numbers which are fixed here, I can decide to use values that will be changing. We want to see what is actually happening, because as you can see, that's what we have is quite confusing. So I will come and introduce this function millis, like that one. This function known as millis will give us time in milliseconds. It will give us the time in milliseconds. So it will give us the time in milliseconds. So whatever it returns, this millis will be saved inside of here. So I will save that one, so that we can be able to understand what is actually happening. So the code has uploaded. So let's go back to the monitor and see. So uh, let's Let's pause it at that point. We already have enough data to analyze. Now you see it tells us task 1 execute each 2000 milliseconds. Now you realize this one is not correct. This is telling us 2000 milliseconds is actually not correct, and I'll be telling you why. So we look at the code. It tells us task 1 executes each, we take millis and we paste it in here. So we know that basically that this one will execute after every 1000 seconds. So we check at that point millis was 2000. Then task 2 execute when millis is at 2037. I will be explaining. I want you to understand why these numbers are reading that way, because we are not we are actually asking for the timing from the microcontroller. Then we see again that task 1 executes at 3000. So what is 3000 minus 2000? It is 1000, and that means that task 1 has been executed after what? It has been executed after 1 millisecond. I mean after 1000 milliseconds, which is 1 second. Then again we see task 1 executes at 4000 milliseconds. So what is 4000 minus 3000? It is 1000. That is after 1 second. Then we see task 2 execute each 4037 milliseconds. So what is 4037 minus 2037? What is that one? That one should give you 2000. Now let's go back to our code. Is our program saying 2000? Yes, of course. And when you go and analyze this data that we are getting from the millis function, you realize that from the pattern that this task is executed after 1 second and this one is executed after 2 seconds. Now someone could be asking him or herself, I mean, why are we seeing 2000? Why are we seeing 2037? So now we go back to the code. What does millis do? Millis is a function. Even in Arduino, we have such a naming of a convention. But basically what millis does, the moment your microcontroller is powered on, pop, the moment it comes on, the moment you connect it to power, millis kicks in. It starts counting the number of milliseconds from when your microcontroller was powered. So it means from the time your microcontroller started executing this code, from here it starts counting. So the reason we are finding that it is showing us 2000, we are starting our timing at 2000 and not at 0, is because at 0 it is when at the top level, when it has now not even started executing everything. Now know that each command has its own latency, it has its own time that it uses to execute. So by the time we are reaching to this task, it means the microcontroller had spent up to 2000 milliseconds, and you can always play with that. If you want to play with microcontrollers timings, you can always like come and maybe you can come and add more codes here in the initializations, and you will see it will affect the timings, the time in which it will show you when you try to print millis inside of here. So it's all about the timing, but again, it does not affect the logic that you write here. Your task will be executed as expected. What just millis gives you is it gives you back, it returns to you the time at that instant. So that's what we have used here to analyze how execution is taking place. So up to that point, is there anyone who feels totally lost, confused, or is not understanding what is actually happening? Or anyone who has any question for that matter? Anyone with a question? Yes. Are we together? Are you guys there? Mm-hmm. Yes. Pardon your question again. Uh-huh. Yes. Yes. Mm-hmm. Yeah. This one. Uh-huh. Yes. This one. Yes. So we have here task 2 execute at 10,038 milliseconds, right? And the last time that task 2 had executed was at 8,037. Now, when you subtract the two, what do you get? You get 2001. So now, what has happened here is now that is not even an issue with kariRS or anything. Now that boils down to the microcontroller. Now the microcontroller can at one time have a slight variation. We are not dealing with high-end CPUs or high-end microcontrollers which have high accuracy. So when the millis function asks the microcontroller to count the time, at that point in time, it returned 1,000, I mean 10,038, right? And the last time it was at 8037. So it just made a slight error variation of up to of 1 milliseconds, which at whatever you'll be executed would be very negligible because of the speed that the microcontroller will be executing. It will adapt very fast. You can see now from that point there was a change. Now it started taking into account. From that point, you can see the microcontroller started using the 38. So it is taking 10,038 and the next time it is going at 12,038. When you subtract them, you get 2,000. So it means at that point, the microcontroller just, after that error, it discovered it and it corrected everything by itself. And that is now the stuff with the microcontroller itself. It's not on the kariRS side, but kariRS just gives you the layer it enters the microcontroller and ensures that no matter what the microcontroller is doing itself, it will ensure that your timing and your logic will happen as you want them to happen. So if you want them at 2000, they will still happen at 2000. So that is what is happening. Have I answered your question? Okay. Do you have any other question? Okay. So if there's anyone who doesn't understand that concept, just ask. And I can answer you because this is a concept. Once you understand it, you will be writing codes that people are in Arduino will be wondering what you're doing because you'll be doing various many tasks with very modular code and without having to do a lot. So I hope even by writing this code, you have been able to now even learn this function known as kprintren. It is the one we use in kariRS to print. If you're in Arduino, they use, what do you use in Arduino? You use something like this, serial don't. printing, something like that. But here we are not doing Arduino, so we are doing kariRS. So this is how we do, and this one is more robust. As we will be going to see, you can do a lot of formatting and a lot of things when dealing with printing stuff to the monitor. Now I want us to move fast. I see the time has really moved, and we need to really cover a lot, because these are the core features that distinguish kariRS from things like Arduino and all that. So now let's now we've seen this is the terminal. Now for the sake of showing you that the printing of this cannot affect this task, I will just uh, comment out this. Now here there's something I want you to take into consideration, and I want you to see it very logically. Do not ever try to have if, for example, this task is named as task 1, and you come and have another name task 1, you'll have a fight with kariRS. And the thing with kariRS, it won't like start shouting at you. You have the freedom to name your functions as you want. What you will get is that you will get execution uncertainties. Things might not time as expected. So always make sure that you name your task uniquely. Give them unique names. You cannot never run out of names. Give them unique names. The other thing, avoid having, for example, this task is scheduled to happen at 500 milliseconds, and then you unaona hapana, nitatengeneza task ingine niite task 2 na niipatie 500 millisecond. Now if you do this kind of thing, you'll basically be doing a redundant work, because okay, you have task 1 here which execute after 500 milliseconds, and then you come and tell kariRS, I have another task 2 which execute after 500 milliseconds. So you're telling kariRS that this task and this task, you should execute them after every 500 milliseconds. So kariRS is like, yo, what are you doing? Like, why don't you just have one task that does all that is executed into this? So this will be something that is redundant. kariRS won't fight you, but it's just redundant. So if a task is supposed to be executed after every 500 milliseconds, just write all the functions you want to be done in one task. This is what we call a task. So let's go back this one to 1000 milliseconds. I hope you've understood. Anyone with a question up to on that concept? Okay. So now I want us to execute this code. Now, this task that I've added here, the carry async, and we have carry pass. Now on itself, it will be turning on and off this, it will be toggling this pin 24. Now if you are to connect a load, maybe an LED or anything to this pin, you'll see it changing state. It will be, and when we talk of changing state, it will be like toggling on and off. So that's what will happen, but it is happening in asynchronicity, non-blocking nature. So these other tasks which are happening here, task 2 and task 3, will not be blocked by this task. So that's what I want us to do. We will be printing, and at the same time we want to see whether our microcontroller will be toggling the pin 24. So let's go fast, and actually when we are doing these things, I want you to think out of the box. Like what we are doing today, as you can see, the session is about the scheduling basics. Like these are literally the basics, but when you want to solve real world problems, now you will be writing code, you'll be writing your logics and all that inside this task, and you'll be able to do a lot of stuff. So let's compile this code and upload it to the MCU. Now the microcontroller I'm connected to has issues with the pins, so let me change it to another one. So because I've changed it, I will need to know where this other microcontroller is connected to. So I carry detect, and we can see it is connected to COM port 11. So so now I can just modify this one to 11, and I just okay, not carry monitor, carry upload, like that. and I'll just click enter, and you can see it more, you can see it compile, and there we go, it has compiled. It has compiled and uploaded the program. So now, since we've dealt with pin number 24, so I want to connect that one. Let me share, let me switch the sharing of the screen so that you can be able to show you. Okay, so I have with me, let me, so I have with me this breadboard which has several LEDs. So I'll be connecting one of these LEDs to pin number 24, and then we can see whether kariRS is actually doing the toggling as expected, and then we'll also look at the monitor at the same time. So let me connect it very fast, and let's see what happens, so that we can be able to wrap up with this session about the timing basics. So we need the ground pin. Pin number is decided to go to pin 24. So now I've connected it. So I want you guys to see this. You can see it that it is toggling, yeah. So now let me share back the full screen. Don't know, because I want to be able to. You guys will just tell me whether you're still seeing the blinking LED. So there it is. So don't know, if you don't see it, you tell me, because now I'm out of there. I'm in the terminal. So now I want us to enter into the terminal. Okay, right now, can you see it? Have I positioned it well? Oh, so okay, maybe that's a feature that when I leave, you cannot see my camera. You cannot see my camera, right? Yes. What's the issue? Uh, okay, like that. You can see it, and at the same time, can you see my monitor? My You can see both. Okay. So now let me. You can you can see my. Okay. I'm only showing the LED. The LED. I'm holding the LED by my hand. Can't you see the? You can see it. Uh, Okay. Why is anyone else not able to see it? Okay. So Wesley, can you see it now? What about now? So what's the issue? Okay. 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 Right now, can you see it? Mm. Anyone, anyone who can see it? Yes. Okay. Can you do what here? The individuals to change their view to? Okay. So they need to pin me. Okay. Can you guys try that and give the feedback? Wesley, are you good now? Yes. Mm, so what's the issue? Francis, are you facing the same issue? Francis can see it. So what is the issue, Wesley? What is the issue you're facing? It seems okay. Can you see my terminal? Okay. So now I can go ahead and run this command, the carry monitor, to initialize the monitor so that you can see whether, so you can see it is blinking the LED, and at the same time it is actually it is at the same time it is actually going on with the printing. So it is continuing to print, yet it is still blinking the LED. If you are to try to use the traditional way of programming, this you would not do this. You will not be able to do this. And if you are to try and do it, you would have latency. Like you would have the printing logic would have to wait for the LED to be on, off, and you would have a lot of inconsistencies and timing issues. And if you want to build a critical system that needs to be very, very accurate, for example, if you want, maybe you are having you want to come up with a prototype for a medical device or something that would need to be in a critical environment, you don't want to be having delays in your program. That is the one thing that's the worst thing you would be doing to yourself. You don't want to have delays. The microcontrollers have to be active. It has to be executing tasks. There's no idling. It has to be busy doing what it is supposed to be doing. Now you do realize now I've shown you that we cannot we have been able to overcome the blocking nature. But now I want to give you another, as we are nearing to wrap up, let me just introduce something new which you can even go and look into. So right now we are having this one LED, so it is turning on and off. And if we were to add more pins, they would turn on and off at the same time. But you might ask me, what if I want to change state in a sequential manner? Uh, you yourself might have a project in which you want like to have to do something like counting, or you could, there's a lot of application to this. So I'll just use LEDs. I'll use for example of an LED chaser. How can you design an LED chaser circuit in an unblocking code? Because it is quite tough to do that. Anyone who has a clue of what you can do? Just something you are thinking of, anything? What is there, anyone who thinks of anything? Okay, right now I just so After showing you what kariRS, are we together, guys? Are we together? We are wrapping up the session. Are we together? Someone to just confirm. So now we've already seen what kariRS does, and to just show you more. For example, here we have pin mode. I could initialize another pin. Maybe someone there is saying, "Oh, we have only seen one LED. What if can't it be go with two?" Let's satisfy someone who might be having that thought. So we could talk of 25 and 26 like that. So 24, 25, 26. Okay. So now we are telling kariRS, we want you to toggle 24, 25, and 26. Let's see what happens if we upload that code. So this is, yeah, let's upload that to COM11. So it is so I told you in kariRS you just ignore these warnings given by Rust. They are just that's because kariRS still in development, so you'll see them disappear in Calvin versions. So they are not something for you to even think about or worry about. So now it has already compiled the code. So right now we are only having one LED. So let me connect two more LEDs as defined in our code. Let me check. We have defined 25 and 26. Let me connect them and then I show you so that we can wrap up with this session. Actually, we have a couple, quite a couple of more things that we need to really do when it comes to learning about the kariRS timing, but we'll continue with them as we continue with the sessions. So I'll connect to pin 25. We've seen is pin 25 and 26. Pin 25 and 26. Where is it? 20. I wrote 26. Okay. So sometimes they have. Let me get a working jumper wire. Okay. Let me explain that in a moment. So okay, I'll be answering to your question right away. So um, So before I answer your question, let me just wrap up on this. So uh, everyone can see these the three LEDs. So yeah, so these three LEDs. Let me. You said I should pin. Let me pin. Yes. So these are what we have defined here: 24, 25, 26. So they are basically what is being toggled. So when kariRS receives these pins, at each invocation of kariRS, we will see it will toggle their state. So you can that's why you can see them go on and off. And at the same time, the monitor can be processing serial data. Now, you have to understand this very important concept because it means uh, you can even beautify your project or be doing something that is just not important in the project or the core while the core processes are taking place. For example, you can be doing processing sensor data and all that other stuff while, let me stop this one so we can see. I want to stop this, kill the process. So it's you can still be doing various tasks, like for example blinking LEDs and processing sensor data, controlling motors, all at the same time. Now a question has been asked again, how is actually this asynchronicity, how does carry async work? Because actually it's very important to understand how is it working. Is it using interrupt, or what is the actual way that all we are achieving this asynchronicity that we are calling asynchronicity. And that's why I began by saying this: kariRS is not and cannot claim to be an altos system because it is designed for one core, so it cannot claim to be that, and it cannot claim parallelism. So what just carry async does, it leverages the time slices of the MCU or of the MPU. So each time, each task, for example, if I can give an example with how a computer works, you have VS Code open, you also have, maybe you have Chrome open, and your computer executes each task of each of that application so fast that it appears like they are happening at the same time. So what carry async does, in the MCU, if the microcontroller is supposed to blink an LED and then do some other stuff, it will do that stuff. But in traditional way, we needed to have, like, you want to have a delay because maybe you want that a particular task, you want it to execute, you need to do some processing, then come back to that task. Now, instead of those time prices places that in which the microcontroller is supposed to be idle, not doing anything, we utilize those time slices. In the concept of interleaving, if you dig deeper into that concept, is what we are utilizing here. So we decide, instead of the microcontroller being idle at this point in time, let it be doing task X, let it be doing task Y. So that's what the MCU is basically doing, and then it appears like we are doing many tasks at the same time. Basically, that's what is happening. So we also have this other part where we use interrupt, and at some point inside the carry async, it is introducing interrupt, but most of the time we are dealing with the interleaving. If you wanted to generalize on how carry async is working, you would generalize it as performing interleaving, or achieving the synchronicity via doing interleaving. So I hope I've answered your question, or you're not yet there. Okay. Now, if you are in C and C++, actually, this is not, you see this code here known as kariRS, this task scheduler, this one. I had, before building kariRS, I had built it in, actually it does exist in Arduino. I had built it in Arduino. It does exist. If you go to the Arduino library manager and you search for Kari, you download that library, you can be able to write this kind of code. What so you can be able to achieve this because the way I had designed it there is that it uses various smart algorithms to just and assign tasks and be able to do the same way in C and C++. But in now here, because the reason now we have kariRS was the main agenda of kariRS was to bring what we are being able to do in C and C++ to bring it into the Rust ecosystem, because Rust itself is growing. It is becoming a sweet spot to enter into embedded system. It is becoming a contender just like C and C++ because of its execution and far mostly because of its safety. But writing Rust code in embedded has been, you know, how to configure the toolchains is an issue. That's why kariRS is here. So it's not like I can't claim that kariRS is coming to replace anything. It is offering another alternative for developers who would like to go the Rust way, who want to go to the safe way of Rust and all that. I hope we are together here, because someone might think, oh, we are trying to fight Arduino. We are trying to fight. No, we are not trying that. Yeah, it's an alternative. Exactly. Thank you. It's like how we have, yeah, it's just another way of doing the same thing. You know what makes kariRS outstanding is like, if you look at things like Platform IO, you look at Arduino, they are all talking the same language. Most of them, you see, it's C and C++. Most of what you're doing. But here we are trying now to bring Rust into to bring Rust to show people, you know, we can do this easier way, even using Rust, and still have safety. We have exactly. So we are trying to get execution and safety at the same time. So that's why we are coming up with kariRS, and we'll be seeing much more of these and having a much more larger ecosystem. So I hope we are together on that. Yes, it's a macro. Yeah, yeah, into Rust code. But you see, also the advantage we have, the advantage we also have with the Rust compiler is that at the time, because of this configuration we have for these files you can see here, of the configuration we've done here, is that at the end of which you'll get the program, the hex file. For example, in AVR we have the hex file. Whatever is redundant will be swept away. You'll have only what is needed. Yeah, because as we will see, as we will continue with these sessions of kariRS, we will see various places where we have macros which have codes which are generated multiple times, but you find that the program will just pick maybe a few of them and the others will be stripped off before the main program is reaches the microcontroller. So we have a lot of optimization and a very good way of making Rust easy to do and friendly for everyone. Okay. Anyone with a question? Anyone else? Um, uh, as you can see, the documentation says that kariRS is open source. So the code for anything you want to see, even this serial, nothing has been hidden. I have released this the code for this framework. So if you want to see how pin mode has been implemented, how carry async has been implemented, you can have a peek. For example, when using VS Code right now, maybe when you using VS Code, that's why I recommend using VS Code. For example, if I wanted to know how carry async is implemented, I would just press Control and then click on kariRS, and boom, it brings me to the implementation of kariRS. Can you see my screen? Yeah, so now you can see it brings me to the implementation of kariRS. It shows me this how kariRS has been and even inside of here, if I want to go deeper into where it is, I click on it and I find this macro, how it has been designed and how everything is working out of the blue. So it's not some, yeah, it is kariRS itself is written in Rust. Everything here is in Rust programming language. Yes, so uh, if because it's also a good thing if you understand this even designing macros, because again kariRS as it grows, it will also need other developers to bring in libraries and whatever, and so it's good if you can also be part of building kariRS. So it's not hidden. kariRS is open source, so you can always check and see how the things are done. So any other question? So now let me introduce just something a little as we leave, but this one we'll talk about it in the next session. So I will another task here. This is where we shall continue in the next session. So I will create a new task here. Let me be very fast, and I will just give it any time after 200, and I will call it whatever. I can call it task 34, whatever name I feel it's okay. You don't have to call it task. You can call it what actually I can call it a sequential task, whatever I want it. And inside of here, I will define something known as carry sequential. This is a very powerful macro, and it has powerful functionalities, and it has the same kind of a signature as, so I call this how do we write it? Sequence one. Okay, I can just call it sequence one. So if, for example, I could try 24, 25, 26. Now let me just comment this one out. Now, if you are to learn this code, this carry sequential is just like carry pass, but what it will do, it will change state of each pin individually. So in the first invocation, it will turn this one on and all these ones off. So it will toggle the state. If they were all off, let's say at initial point they are all off, so it will change the state of this first one to high and not tamper with this other one. Then on the next invocation, it will change the state of this one. If it was low, it turns it to high, and this other one is turned to low. Then on the next invocation, it goes to this one, and after it's done, it goes back to the start. So by doing that, you will have a sequential toggle. So that is how you can implement something like a chaser LED circuit. So if you already have a microcontroller, you can go ahead and play with such kind of code of carry sequential, and I'll be talking about it and showing how it works come next time, or in the other sessions. So is there anyone who have any other question or something that you want to ask before as we wrap up this session? I think that will be all for today. Anyone with a question? I have recorded the session. Yes, I will be sharing the link to this session in the WhatsApp group link, or in the WhatsApp group. Yeah. So if that's all, then I thank you all for attending, and I see you next time.